Welcome to Unit 3. In this unit we'll be looking at matter as solutions, acids, and bases. For your outline, it's going to be chapters 5 and 6 in your Inquiry into Chemistry textbook. And we're going to get right into solutions. So we'll talk about classifying solutions, and this is pages 158 to 175 in your textbook. So when we talk about matter, it sometimes helps to classify matter based on some of its physical properties. So far, most of the matter we've been talking about are pure substances. So we spent time talking about compounds and elements, the difference between the two, and I guess here, these consist of only one type of molecule. Would be one way to classify it. For molecules, molecules can be broken down if they're compounds by heat and electricity. Molecules that consist of only one element cannot be broken down by heat or electricity. So those are the two types of pure substances. The other type of substance would be a mixture. Mixtures are variable composition. We can think of things like gravel would be a good example of a mixture. Milk is a mixture. It has solid particles suspended in a liquid. We could even think of something like Kool-Aid. If I could spell Kool-Aid, it would be better. Acids and bases in solution. So things that consist of more than one type of molecule is a mixture. So more than one type of molecule. The two types of mixtures that we can discuss, the first type, or I guess we'll do the second type first, are heterogeneous mixtures. These mixtures have different properties in small samples, or often you can see that certain parts of the composition consist of consist of one molecule in a greater quantity than another. For example, gravel fits this. If you take little samples of gravel, some of them are going to contain some rocks and some dirt, and other samples will contain different rocks and maybe different types of dirt. So gravel would be a heterogeneous mixture. The other type of mixture would be a solution, and these are the ones we're going to be talking about in this unit. These are homogeneous mixtures. They have the same properties throughout. You can tell you're dealing with a solution if it is clear, usually. So if something is clear, so for example, Kool-Aid would be an example of a solution. Sugar water, salt water, coffee would be a solution. Tea would be a solution. So those are examples of solutions. So now that we've kind of talked about what solutions are, we're going to talk about what happens when we put certain types of compounds in water. This is how we make solutions of a certain type. So ionic compounds, when we put them in water, water is the solvent. The ionic compound would be the solute. Most, but not all ionic compounds are soluble in water, so they will dissolve. To determine if they are soluble, we can use our solubility table. Now this only works if your solute's water, or if your solvent's water, sorry. And the way we read this table, it looks a little more confusing than it actually is. But, here we go. This row is soluble. And this row is insoluble. So in the column here, one thing says very soluble, one thing says slightly soluble. For us, that slightly soluble really means insoluble. And to use this table, what we're going to do is most of the time you're going to find the negative ion from your compound in the top row. So if you take a look at this top row, you can see that most of the ions listed are negative ions. So here there's a list of ions. most of them are the negative ions. Fluoride, the rest are halides, sulfate, sulfite, phosphate, and so on. So that top row contains negative ions. So you're going to find that ion in your compound, and then you're going to find the positive ion in the body of the table. So for example, and I will do some examples on the next page, and it'll make more sense. So we'll just look at the steps now, and then we'll do some examples. If the compound, or if that positive ion is in this soluble row, then the ionic compound is soluble. If the positive ion is in the insoluble row, then the compound is insoluble. And note there's also a couple exceptions there, but we'll get to those in the examples. So here's a couple of examples. So if we want to find out if magnesium iodide is soluble in water, the first thing we do is we should always know what our compound formula is. So it's going to be MgI2. And so iodide is a negative ion. So we take a look at our table, we find iodine, and then we take a look and see where magnesium is. And if we look in this top row, we see that it says most. So most positive ions, when they're in compounds with iodine, are very soluble, or they're soluble. When we look at this second row, or this last row, it gives a list of all the ions that are insoluble when they're in iodine compounds. So copper iodide, silver iodide, mercury iodide, and this is mercury 1 iodide and mercury 2 iodide, and lead iodide, so we lead 2. If one of these ions are the ones we're looking for, then we have an insoluble compound. But since we're working with magnesium, magnesium iodide would be soluble. So we can put a little AQ beside it, or to let us know that this magnesium iodide has dissolved in water. Next we'll look at iron 2 fluoride. So again, we find our negative ion, the fluoride. It's here. And then we take a look at our two rows. Most ions are soluble when they're with fluoride. This list in the second column, or the bottom row, shows us all of the ions that are not soluble when they're in fluoride compounds. Since iron's not there, we can say that iron 2 fluoride, or Fe, F2, is soluble, so we can put a little aqueous beside it. For calcium phosphate, same idea, we find the negative ion. So calcium is a 2+ ion, phosphate's 3-, so we would have Ca3, PO4, 2, and we'll take a look. Here we have phosphate. Now this one is kind of switched. In the top row are all of the ions that form insoluble compounds with phosphate. When we look in the bottom, we can see that most of our carbonate, phosphate, and sulfite ions form insoluble compounds with one exception. We don't have the exception. So this compound is insoluble. And so we put an S beside it. This means even when it's put into water, it doesn't dissolve. It sits at the bottom. It would be a white powder sitting at the bottom of the test tube or the beaker. So it's insoluble. So we put a little salt beside it to say that it didn't change. Next we'll try silver 1 chloride. So again, we look for chloride in our table. I can't find there it is. Alright, so there's chloride. We take a look. Most things are soluble when they're with chloride, and then we check our list. Copper 1, silver 1, nay, silver 1. So what this means is silver chloride is insoluble. So AgCl is solid when you put it in water. Calcium sulfate. So same idea. We find sulfate. There's our sulfate ion. And there's calcium in the second row here, so it means it's insoluble. So the CaSO4 will remain solid in solution. Lithium sulfite. So we got to find our sulfite ion. Here's sulfite. We take a look. Hydrogen, sodium, potassium, and ammonia. These things form soluble compounds with sulfite. Everything else forms an insoluble compound. Note there's an exception here. Lithium carbonate is actually soluble. So lithium with carbonate is soluble, but lithium with phosphate and sulfite would still be insoluble. We don't have the exception. We have lithium phosphate. So Li2SO3 is solid or insoluble. When we look for molecular compounds, we don't have a table, but generally they're insoluble in water. Compounds with only London dispersion, and here we got to remember what kind of intermolecular forces they have. If the compounds only have London dispersion forces, they are insoluble. Slightly polar substances are slightly soluble, and substances with hydrogen bonds are generally soluble in water. So when you're looking at a molecular compound, you got to decide what kind of intermolecular forces are in that compound, and then that will tell you whether or not it's soluble. Another difference, or another quality that some solutions have, is the ability to conduct electricity. So all aqueous solutions are transparent. You can see through them. They're not murky. So, example, something like milk is not a solution because it's opaque. You can't see through it. Compounds that dissolve in water and conduct electricity are called electrolytes. And so empirically, here's what we found out. All ionic solutions conduct electricity if they're soluble. So if an ionic compound is soluble in water, it conducts electricity. Molecular compounds never conduct electricity even when they're soluble. So for example, a salt solution, something with NaCl, it's aqueous in solution and it conducts electricity. So it conducts electrons. If we look at a sugar solution, so C12H22O11, so this is table sugar. If you put sugar in water, it dissolves, it disappears in the water, it becomes transparent, but it does not conduct electricity. So there's a big difference there, and so now we got to talk about, well, why do ionic compounds conduct electricity when they're in solution, and why don't molecular compounds? And now we got to look at a third type of compound here. Acid compounds are kind of strange compounds. Acids are usually molecular substances. So for example, if we take a look at hydrochloric or hydrogen chloride, we name it as if it was ionic, but really we know it's not, because all ionic compounds are solid at room temperature, and hydrogen chloride's a gas. So we know it's molecular, we know it shares electrons between those hydrogens and those chlorides. So they're molecular compounds, but, and this is why we know, they can be solid, liquid, or gas at SATP, so we know they have covalent bonds. We know they dissolve in water because they're polar compounds, but they are also electrolytes. It turns out that these acid compounds, they're so polar that when they do enter water, they actually ionize, or they form ions that become electrolytes. So, when acids aren't in water, we treat them as if they're molecular compounds. When they are in water, they act more like ionic compounds. And so, this is what our acids do when you put them in water, which means they act like ionic compounds. For bases, ionic compounds that have a hydroxide ion, those are bases. They're all solid at SATP, so they look like ionic compounds, they act like ionic compounds, and so when you put them in water, they behave like ionic compounds. And if you notice on your solubility table, there is a column, the last column on the table is for hydroxide ions. So if they dissolve, they will conduct electricity. For acids and bases and pH, pH is a unit of measurement that reports the acidity of a solution, and some of you have probably heard this before, some of you maybe not, but the scale goes from 0 to 14, and generally speaking, acids have low pHs, their pH is below 7, and bases have high pHs above 7. If something has a pH of exactly 7, then it's considered neutral. And pH can be measured using litmus paper, a pH meter, or indicators, which are chemicals that change color in a solution of a specific acidity. When we're naming acids, by convention, acids can be written as H acids or COOH acids, and the difference is these COOH acids are organic acids, and these are just molecular acids. Now, for the organic acids, most of the names are memorized, and we'll talk about a naming system for these. This is the naming systems in Chem 30, actually. So we'll be given the names as we need them. For the hydrogen acids, or the H acids, there is a naming system for them when they're put in water. So in these ones, most of the acids you have in your data booklet, you can find in your data booklet, and this is in the 2008 version. Most of the acid names that we use, you can find on page 8 and 9. So in your 2008 data booklet, pages 8 and 9 have most of the acids that you need to know and their names, but it doesn't hurt to get familiar with the general idea of how an acid is named, just because it speeds up your ability to go from a name to a formula. So, if the name of the substance is written as an ide substance, so if it's just a negative ion off the periodic table, then it's going to be a hydroblank acid. So here's an example: hydrogen HBr. This is bromine. So in a compound, it's bromide. So the acid would be bromic. If the ionic name is a hypo, so if it's a polyatomic ion that starts with hypo, so for example hypochloride, then it's going to be sorry, bad spelling. Here we go. Let's try this again. CH. Okay, let's try that again. Oh, I'm going to get my eraser turned off here. Okay, sorry about that. So if it is a hypo acid, so for example, hypochloride, it will be hypochlorous. If it's a hydrogen ite, so if it's a polyatomic ion that ends with ite, for example, sulfite, then it will be sulfurous. 8 acids, for example, hydrogen nitrate, so will be nitric. And per 8s, so for example, hydrogen perchlorate will be perchloric acid. So it takes a while to get used to, but that's the naming scheme for acids. And like I said, most of them are in your data booklet on page 8 and 9. So knowing the naming system isn't critical. So for definitions, solutions are defined as, so we have a bunch of solutions so far. We have ionic solutions, molecular solutions, acid solutions, base solutions. So solutions are defined as mixtures composed of a solute and a solvent. Solutes and solvents can be gases, liquids, or solids. Most of the time, for us, 99% of the time, maybe even more than 99% of the time, our solvent will be water. our solute will be some kind of ionic or molecular or acidic or basic compound. So at 99% of the time our solvent's going to be water, and our solutes are usually going to be solids. We usually talk about solids and compounds, although sometimes we do talk about gases. Solvent is the thing that's present in the largest quantity. And so when we talk about solutions, the water is usually in the largest quantity. We usually have more water in that mixture than anything else. The solutes are the things that are in smaller quantity. If a solution or if a mixture is milky, translucent, so not totally clear, or opaque, that means they have undissolved chunks in them, and so they're heterogeneous, because technically speaking, we could grab little samples that would have more solid chunks in it than other samples. So since they have variable composition, they're mixtures. So for water solutions, it's the most common solution where water is a solvent. Because it's so common, it's given a special name, aqueous. So if something's in water, it's said to be in an aqueous solution. And water is kind of special. It's a special solvent, if you like, because it's able to dissolve so many substances, both ionic and molecular substances. Okay, so dissolving is a physical change, and it's not a chemical change. So even though it looks like, and we're going to be separating things apart, things are going to be breaking, but because it's easily reversible, it's considered a physical change. And what's happening is bonds are being broken, and again being put back together. So the bonds being broken are the bonds holding solute ions or molecules together. So the bonds that are being broken are ionic bonds or intermolecular forces when we put things in water. And there's also going to be breaking of bonds in the solvent. So those water molecules, remember, water is a polar compound, and so water molecules are attracted to each other by hydrogen bonding. Some of those bonds are going to break, and because the water is going to become more attracted to whatever we just put in there. So we're breaking two sets of bonds to form bonds between particles of our solute and particles of our solvent. And here's an idea of what we're talking about. So when a solution, or when a solute, dissolves in a solvent such as water, there are three processes that are occurring simultaneously. The first processes are the breaking of the hydrogen, ionic, and intermolecular forces in those compounds. So, for example, when we're dissolving water, that was good. When we're dissolving sodium chloride in water or salt in water, two things are happening, or three things are happening, but we'll talk about two first. Those ionic bonds in the salt crystal are breaking apart. Chloride ions are separating from sodium ions. There are also bonds breaking in our water. So water molecules, they're hydrogen bonding. They're going to start becoming attracted to these positive and negative ions, the chloride ions and the sodium ions in the water. If you take a look here it's showing water molecules gathered around a sodium ion. So notice that the oxygens, that's the big black dots here, and I apologize for the lack of color, but in the center here, there's a sodium ion. The sodium ion is going to be positively charged, and it's going to be attracted to those negative ends of the water molecules. Now, the breaking of bonds is endothermic. It takes energy to break bonds. The formations of bonds is exothermic. Once bonds are made, energy is released. So the bonds being made are the bonds between the water molecules and our positive and negative ions. In molecular compounds, the same sort of thing is happening. Water molecules are coming down, and they're attracted to one of our sugar molecules, because the sugar molecules are polar. They have OH groups on them, so they're going to be polar. And as a water molecule comes down, it can grab onto one of those sugar crystals or one of those sugar molecules. And if we take a look at the picture below, we can see here that a bunch of water is being attracted to a sugar molecule. So the top process is endothermic. Energy has to be, or energy is absorbed when these bonds are breaking. As bonds are being formed, this is an exothermic process and energy is being released. So when things are dissolving in water, there actually is a temperature change in the solution. And whether or not the temperature goes up or down depends on which process requires more energy. So if breaking the bonds in our solvent and our solute takes more energy than the energy released when it dissolves, the temperature is going to drop. So it'll be an endothermic process, and the temperature of our solution is going to drop. It's going to start at room temperature, and then it's going to feel colder as it absorbs energy to make those bonds. If the energy required to break the bonds is less than the energy required to form new bonds, the process is going to be exothermic, and the temperature of the solution will rise. So here's an example. When you use a cold pack for an injury, it actually consists of two chambers, one containing an ionic salt, the other containing water. When a cold pack is being used, it's smashed or smacked or cracked or bent, and that actually breaks the container so that they mix. And the water and salt mix, and the salt dissolves in the water, and the cold pack becomes cooled. So we're going to talk about why this happens, or give a few notes as to why this happens when something dissolves. So the first step is ionic bonds in the salt break. And the hydrogen bonds between water molecules also break. There we go. Okay. The next thing that's going to happen is bonds are formed between the water molecules and the ions from our salt. So these two things always happen when an ionic compound is dissolving. But here's what here's how we explain the temperature change. Since the temperature is dropping, we know the energy required to break bonds is greater than the energy released when the new bonds are formed. If it was a hot pack, it would be the reverse. When you break a hot pack, it has an ionic salt and water. When they mix, that ionic salt actually, the energy required to break the bonds is less than the energy released when the new bonds are formed between the ionic compound and the water molecules, and therefore heat's given off. The solution heats up, and you have a hot pack. So, ionic and molecular compounds in solution. They're both aqueous solutions. They're transparent and often colorless. Sometimes they'll have a color to them, but usually not. For example, if you look at an aqueous sugar solution, an aqueous salt solution, and an aqueous vinegar solution, they all look the same. You can't tell which is which just by looking at them. You'd have to smell them or taste them. but they have some properties that are very different. And one is conductivity. So salt solutions conduct electricity. These are our electrolytes. The sugar solution does not conduct electricity, so these are non-electrolytes. And the vinegar solution, it conducts electricity, but not as well as a salt solution. So it's also an electrolyte, but it's a weak electrolyte. So we have to be able to explain why these three solutions that look the same behave differently or have different physical properties. So we'll start with the ionic solutions, and we'll have to go with our good friend Arrhenius. He said that electric current is caused by the movement of charge. So it's caused by the particles. Our charged particles have to be moving in the solution. Now we've said that electrolytic compounds dissociate in water or they form ions. And this can be represented with a dissociation equation. So for example, ionic compounds, when they dissolve in water, if they dissolve in water, they form ions. So the first three examples, sodium chloride, sodium sulfide, and strontium 2 acetate, all dissolve in water when you put them in water. They are going to break apart into their ions. And notice that the ratio between molecules on the left side and right side has to remain the same. So in the first compound, there's one sodium ion, or one sodium for every chloride ion. When it dissociates, you get one sodium for every one chloride. In the second compound, there are two sodiums for every one sulfur. So when we dissociate it, we have to have two sodium ions to every one sulfide ion. And same thing here, and I missed it in my notes. Here we go. There should be a 2 right there. There should be 2 acetate ions for every one strontium that's produced. For compounds that don't dissolve in water, so for example, barium sulfate, it doesn't dissolve in water, so it doesn't dissociate. You don't write it down as ions because it didn't actually break. Now, molecular compounds, they don't conduct electricity. Therefore, they don't dissociate. If they did dissociate, then they would conduct electricity. But since they don't, they can't dissociate. So when we put a molecular compound in water, it's aqueous, but it doesn't form any ions. The molecules are still whole molecules. In this case, it's a sugar molecule. All the carbons and hydrogens and oxygens are still all bonded together as one unit. So it's aqueous, but it's not ionic. It doesn't dissociate. For acids, since they conduct electricity, and since acids ionize to form hydrogen ions, we know that they form ions in solutions. So when we have an acid compound, when it's in water, we dissociate it. We write it down as a dissociation reaction. So here's an example. If the following substances are electrolytes, then we're going to use a chemical equation to illustrate it. So what I would do is, if you have the notes in front of you, I would go through your solubility table. Pause the recording first, sorry. Go through your solubility table and just check to see if you can tell if these compounds are soluble first. And if they are, write down on a scrap piece of paper or on the notepad if you're brave, and write the dissociation equation. Once you have some answers, unpause the show and see if you agree with me. So that way you know if you're getting this down okay. So I'll pause it now and then write a few down. And hopefully you've done that. Now you're back, and we'll go through and we'll see. So the first thing we do is we write down our chemical formula. So here we have silver chloride. So it's going to be AgCl, and it's solid when it's not in water. When we put it in water, we write the H2O over the arrow. And then what I'm going to do is just check my solubility table in my data book. And when I find the chloride ion, I take a look, and silver is in the bottom row, which means it's not soluble. So we'd write it as AgCl solid. Nothing happens to it. If you put it in water, it just sinks to the bottom and sits there. Now we'll check potassium sulfate. So same idea. First we need a chemical formula. Potassium's a 1 plus ion, sulfate's a 2 minus, so it's going to be K2SO4, and it's solid when it's put in water, and so we'll put water over our arrow. And I find sulfate, I take a look. Most ions, it says, are soluble when they're with sulfates. There's a list of ions that aren't, and potassium's not in the list. So we know what ionizes. So because there's 2 potassiums for every 1 sulfate, we write 2, and this is a K, and it's K plus, so we write it down with its charge. And the charge we just get off our periodic table. Sodium forms a 1 plus ion, so we write it down as a 1 plus ion. Sulfate is a 2 minus ion, so we write it down as a 2 minus ion. And there we go. That's what happens to potassium sulfate in water. Sodium hydroxide. So again, first thing, always get the formula. Sodium's 1 plus, hydroxide's 1 minus, and it's an ionic compound, so we know it's solid at room temperature. And then we drop it in the water, and we take a look at our hydroxide. So hydroxide, there's a list of ions that are soluble, and sodium's in that list. It's the second one down, so we know it forms ions. And since there's 1 sodium for every 1 hydroxide, we just write down each ion, and there's our sodium hydroxide. Hydrogen fluoride, same idea, first things first. Hydrogen fluoride is HF. Now, it turns out the hydrogen fluoride is a gas at room temperature because it's a molecular compound, but we should also recognize this as being an acid, and we said acids are soluble in water. But even if we didn't remember that, we could check our solubility table. Fluoride's on the list. If we take a look, most things with fluoride are soluble. There's a list of things that are insoluble or slightly soluble. Hydrogen's not there, so we know this is H plus aqueous plus F negative aqueous. Last one, methanol. When we see methanol, this is a molecular compound. So now that we know it's molecular, there's a couple things we can do. When you see an OH at the end of something, if it's just an OH, now you might be tempted to call this a base, but because it's a molecular compound, it's not also known as it's liquid at room temperature, so we know it doesn't behave as an ionic compound, and it's not an acid, so we aren't going to treat it as an acid compound. So we know that it's CH3OH liquid to begin with, and the question is, when we put it in water, will it dissolve? Now, because it's an alcohol, you might be aware that it just does. Ethanol dissolves in water, and so it makes sense that methanol would as well. If you're not sure, it doesn't hurt to go back to your Unit 1 skills and draw yourself a methanol molecule. Whoops, I want an H on this side just so that I have room. And there's our methanol molecule. And what we should see here is, here we have hydrogen bonding, or a very polar bond. So, because it's a polar substance, it's going to dissolve in water. So because it has a polar bond, and it only has 1 polar bond, so it's not going to cancel out with anything else, it will dissolve in water. And so we write it with an aqueous. Note that we don't dissociate anything because molecular compounds don't dissociate in water. That's it for this lecture. We'll see you in the next one.